Hi everyone. So today I'm talking with one of my colleague at work actually, and he's working on a project which is in the SLAM robotic project. It's an autonomous project that he's working on that in his free time. So I would like let's talk to him and please let us know, Eric, what are you doing currently?
Yes, I I come from a robotics background, so I studied robotics in university in the past, and have been working on some robotics as a professionally. But now I actually am working on a project with autonomous robot, a four-wheeled robot, and the purpose is to solve this problem, which is called SLAM, so simultaneous localization and mapping. So what this means is that there is some type of robot that needs to create a map out of its surroundings. So usually this can be any kind of map, but usually it's some kind of point cloud. So some points in space that it needs to generate based on the surroundings, which describe the physical space around it. So that's one part of this problem, and the second part of the problem is to localize itself, because since the robot is creating a map in this global coordinate system of the world, of some global coordinate system, it observes some features in its surroundings, for example, with a camera or with a lidar or something like this, some kind of sensors. And these are observed in its local coordinate system. So it needs to somehow locate itself in this global coordinate system in order to know how to map these in the in this mapping. So it's that's why it's called simultaneous localization and mapping, because it solves these two. The problem is solving these two problems at the same time,
Okay.
and this so the reason why I'm doing this is because I just find this problem interesting, and robotics in general, because it deals with physical um, with the a chaotic real world scenario. And I think you have to, it's not very clean, it's sometimes very chaotic, and you have to be creative to find solutions to these things. So so at the moment I'm just starting with baby steps. So the first problem is to just create some kind of 3D model for this. So I can maybe explain the system I'm dealing with. So what I'm building, what everything is based on is I have a small computer. It's BeagleBone Black, which has this robotic scape, like a add-on. So BeagleBone Black is like a Raspberry Pi or some smaller um, Linux-based computer, and it has this robotic scape as an add-on for this board. And this contains a lot of sensors. So we have a IMU, inertial measurement unit, I think. So this consists of different sensors for detecting motion. So this is, for example, a gyroscope detecting the angular velocity, and accelerometers for detecting acceleration, and a compass as well to detect orientation. So this is the sensors I have, and then in addition to this, I also have a camera, a very basic web camera. But this so uh, so I am using this IMU for detecting, for estimating the motion of the robot. But then in addition to this, I have this camera feed as well, so such that I can make the estimate more robust. And also, this is responsible for creating this map of the environment, because the robot observes different features on the RGB image feed, and based on this, it needs to it uses these features in order to map its environment.
Okay.
And yeah,
Can
so
I have a
that's basically
question?
just it. Yeah.
Sure. So, thanks. It was quite comprehensive. Can I ask that what type of slammer are you going to use? You told about the camera. You told about I don't know, IMUV like gyroscope and etc. So can we say that it's a visual slam? It's a lidar slam? It's an RGB D slam? Or it's a graph-based SLAM. So what exactly type of SLAM you want to use?
Yeah. So that this is a little bit open still, but this particular problem that I'm solving, it's called a monocular visual SLAM. I think it's uh, the definition of the problem itself, but that leaves the algorithm itself quite open. So SLAM is not necessarily like some specific algorithm, but it's so this is still open for me. So I'm still investigating this, but at the moment I'm the first baby step I'm taking is
Mm,
to only estimate the position or the movement of the robot based on this IMU. So I start with this, and with this extended Kalman filter seemed like the first approach to use, and I'm using this as the first step to see if I can at least get some kind of reasonable estimates for the motions for the movement of the robot.
mm,
And then so I've looked into these things, these different algorithms, and the one for this visual part, so this is really not based on very extensive research, but I've this orb. There are features called orb features, which seem to be used quite a lot because they are quite computationally efficient and seem to be have been used in a lot of SLAM applications. So this might be the first step, but I'm not sure yet. So yeah, that depends a little bit. So I need to research more on it.
okay, yeah, cool. And do you know that, of course, it depends probably on the application, that's which way you decide to go and what is your intention, like what exactly? So I think it's an open door, as you said.
What the application? So it's that's a good question. So I'm using this more for my own personal interests to and to develop my own expertise in this. So it's just I think if you learn, even when you learn the theory in university, and so it's you never clearly understand it until you have to implement it, or at least you understand it on a different level. So that's one thing. So that's the main goal. But I guess yeah. So there could be a lot of different applications. I guess many of these vacuum cleaners use some type of SLAM for finding their way inside of the home, and ensuring to that they cover all the surfaces inside of the home. So that's one application. But there are also, of course, in recent times, these military applications have come into the
Mhm.
picture. So that's also a little bit more controversial topic, but that's one thing. Um, then or or these rescue operations where you can send a human being. But this is of course this system I'm developing is of course very limited in its scope. So this is only for indoor environment, and of course since we are dealing with the camera only, it has to be it relies on light. So
Mhm.
the lighting conditions are important for this to work reliably.
Mhm. I mean, like, I've had several generation of Roomba. So each generation, the older generation did not have any camera, so it was only working based on infrared sensors.
Yeah, yeah,
So, but when I just put them together, like turn them on, every one of them, it is completely clear to me that each of them had a separate, different algorithm to start. Like the very beginning, like the very, let's say, older version, they just start and try to make a circle and they make the circle bigger and bigger until they reach to the walls or whatever. And then they
yeah,
try to change the way or like make it perpendicular or I don't know, going different way. But the camera way is much more smarter. It goes to the corners and tries to like find the most optimized or let's say optimal way to follow, avoid any like let's say contact with the objects.
yeah.
So you can see the progress and you can see the progress in the algorithm based on the sensor development as well. So it is really nice to just watch the progress, especially for the vacuum cleaners.
Yes,
Um, so I think that
yeah,
this is something to learn about. Maybe that you do not need to repeat. Maybe the way that the people has done, like the work that people have done already, and take some ideas.
yeah. That's that's interesting. Yeah, and the cameras. Um, yeah, I guess they are more flexible because they contain more data that can be used in different ways. I think LiDAR is also has the advantage that it maybe has can give more accurate distance measurements. The camera, since we are not getting the distance measurement directly, we have to somehow create intelligent algorithms to deduce this based on the camera data. But I guess we can be more flexible with the camera, and it's also very cheap. So I also thought about this LiDAR approach, and it's also quite expensive, and I think I can get more creative with this camera
Mm,
RGB data.
yeah. And probably also there is a need of sensor fusion that you take from different perspective or different data from different sensor and try to match them in a way that you can get more complete picture of the surrounding.
Yes.
But I think you can at the moment stick to the to your primary plan that is camera.
Yeah, yes. Yeah, in a way, this is kind of sensor fusion already because I'm fusing a lot of different sensors. So this
Hmm.
IMU and the
Of course.
encoders of the wheels, and then
Yeah,
this
okay.
camera. But uh, yeah,
All right. Um, let's talk a little bit about the mathematics. You told about the Kalman filtering. What is that? We don't need to really go to
Mm.
details, but what does it do? Like, can you explain that? Why you mentioned actually Kalman filtering?
yeah. So it's one sort of sensor fusion algorithm where if we have different sensors which measure different things, it's possible to and if you also have some kind of model of the world or some model that describes describes the robot or whatever you are trying to measure or understand some system. Then with this, it consists of two parts. So there is one prediction step where this state model is used. So this is a state transition model. So it's some kind of matrix which describes this state, this model, and then so getting from a state, getting from how the state changes based on the control inputs that you give. So these control inputs can be whatever you want to define, in which are part of this system. And then in this prediction step, so what it does is it uses this state model that you have predefined, and it is kind of a constant thing that you have defined, and then it uses this to predict where the system is in the next state. And then there is another step of this filter, which is called the update step, where another set of sensors which are used to measure some measurements of some other sensors, or and then it updates based on these measurements, both the uncertainty of where the uncertainty of this estimate, and then also the state. So it uses this prediction and update in tandems. It can be even on different frequencies, but you can do like several prediction steps and then one update step, or but basically the idea is that you are getting closer to the truth with this update step, and then so what you get in the end is both the state estimation, the state estimate, and then the uncertainty of this, and this updates continuously. Then this is the Kalman filter. So then we have the extended Kalman filter, which is the same thing basically, but it's just if you have a nonlinear system. So there it is useful for that, because the Kalman filter works only if the system is linear. So as soon as you're dealing with some kind of angles and stuff like this, where you need to use cosine or sine or something like this, which are not linear, then you kind of can't use the Kalman filter anymore. So it's only for quite simple systems, but I'm not sure. This is actually the first time I'm applying this in a real, like implementing this in a real project. So I need to. It's a learning process for me, but yeah, that's the basic principles as far as I understand it.
Okay, no, very cool. So if you want to implement the Islam, do you want to implement it in Python or ROS, or what is exactly that? Where do you want to implement it?
Yeah, so at the moment I have the I have implemented it in C++ for the first prototype, but then I realized quite fast that since it's very slow to do these iterations when you are testing new things, and the project is very changing a lot, and these computational resources of the machines or these computers that I have are very limited. So I ended up spending a lot of time just waiting for it to recompile. So I find that Python is much more faster to iterate and prototype test different prototypes. So that's what I'm using now.
Mhm.
And this, I'm just trying to get some kind of prototype such that I can then maybe later write it in C++ if it's some kind of, if there's some limitations with the computation.
Yeah.
But that's what I'm using. So more or less C++ and Python. Um, and you can get just with this NumPy library, you can get quite a lot done.
Yeah. Yeah, of course. And so I have some experience in Python programming regarding motion control. So it's actually quite good. I'm happy with that. So, but for Slam, I have no experience, so I cannot say anything. Um, yeah, we will see. But I guess your
Yeah,
plan is actually to implement it and to really build this prototype, right?
yeah, exactly. So I have now started just with another colleague to create the first 3D model of this, such that I can install all the computers and the camera, and then also the wheels, of course, and that's so I'm doing implementing this on a real physical system. Yes, it's not a simulation only thing. It's a real system.
Mhm. Nice. Um, can you just a little bit tell me that what is the difference between SLAM and pure odometry? So, why you not, do not use a pure odometry for your project? Why you want to use a SLAM?
Yeah. So as I understand, pure odometry would be to use only, I think, the wheel encoders for determining where the robot has moved, and this might work to some extent. But the problem is that if there is any errors, long-term errors where the robot it's prone to drifting. So if uh, errors add up over time, and then the estimate of the position of the robot can drift a lot, and or more or less it will drift, and then that's a reason to use some kind of other feedback, like the 3D, the camera, such that it can update its estimate, so that this drift um, can be reduced, and the position updated, such that this works in long term.
Yeah, okay, that makes sense, of course. Of course, if you're just testing it at home, so there should not be that much constraint for your robot. Maybe a pure odometry also works fine, but yeah, but if the train is a little bit challenging, then definitely you need other aspects to double check or estimate if it's working fine or not.
Yeah, I think there's so much noise in the sensors, and there's a lot of things that happen in the real world, which even when you have a perfect system, seemingly perfect system, where you have no like factors, seemingly no factors that would result in errors, yeah, there will always be some um, imperfections, and this will over time add up.
Yeah. So as you said, I think that Islam basically is challenging in general because sensor noise is one of them, as you said. Then I think you have the problem of real-time computation. So I don't know if how you want to manage the real-time computation. You said that you have prepared your hardware, but yeah, I think
Yes. So I don't have very powerful computers.
yeah.
So at the moment, actually, I'm using two computers just because it would be nicer to only use one, but just uh, I have this BeagleBone Black with a robotic escape to control the motors and get the sensor data from the IMU. And then I have a BeagleBone AI, it's called. It's a more powerful computer, which also has some kind of basic GPU. So it should
Mhm.
be better for processing image data. And the reason why I'm having two computers is that um, just to get faster ahead, because in theory I could connect this robotic scape with all the sensors and the robot controllers to the BeagleBone AI, which processes the image data. But it's kind of it was a mess for me to even get this to work with Linux images and stuff like this, which are not always necessarily compatible. So you have to do a lot of things underneath in to get some device trees, the
Mm.
correct device trees up and running and so on. But I didn't want to go into this rabbit hole at the moment, so I just used these two computers instead because I had them already on hand. And the BeagleBone Black is basically, I realized quite early on that it wouldn't be able to handle this
Competition.
stream of image data, and on top of that, do a lot of processing with SLAM. So I needed to get something more powerful. So that's why I'm using BeagleBone AI.
And how do you connect these two boards together? It's like via Wi-Fi or?
So they are connected via Ethernet. So they
Ah,
talk, and then they talk with each other with CMQ.
CMQ port. Okay, cool. Um, so I think one of the other challenges that you probably face is the loops. So it could happen that a lot of time that you recognize you have been somewhere that you have been already before. So
Mm.
when the robot moves, then you know that is it new or it is again in the same loop that I was before.
Yeah,
So
right. Yeah.
so this is something that is actually I don't know how to avoid these loops in Islam-based motion. Or do you want actually to avoid? Like it depends really if you want to repeat this loop or you want to just just once to identify and then
Yeah,
never.
I'm not sure. So I have just on the surface seen these loops concept, but I think it's not a problem. It's just something that I need to identify. So
Mm.
I need to. The problem is identifying when you have reached the same spot again, which you already were previously. And this is just the it's just important to be able to recognize this, because otherwise you will end up creating some map, which is some new map, which is actually something you already see. So you have to update it in order to detect the loop, in order to know update also your position of the robot, such
Yeah,
that yes. So yeah, this will be interesting for sure. I will. I'm sure I will find out about it when I encounter it. But at the moment, I don't have very
yeah,
deep knowledge about these loops.
sure. And I guess that basically all the robots that have developed during the last years, they have tried to monitor and explore the environment as much as possible, create these nodes or mapping the nodes and the physical nodes in the environment. Then I think like of course the physical obstacles, physical objects, they can move, but let's consider the criteria for autonomous vehicles. Like if they go on the streets, of course the streets will remain the same, the housing, the buildings, everything probably remains the same place. They don't quite change. Of course, the cars will move, people will move, so these are clear. But the structure of the road will always be the same, I guess. So that makes quite sense if you many times let this robot just explore the city and just see what's around, what is the surrounding. So it will step by step can complete the idea of node mapping. Do you know what I mean? Like it is like a learning process for the robot to understand or make the picture of the environment um, perfect, more perfect.
Yeah. So it's I think that yeah, it's a continuously it will update. It's both the map itself and its own location. So it will kind of self-correct this when it gets more information.
Mm.
But the hope is that it actually doesn't that it works robustly, and this could be very challenging, I guess, because it's very messy. There's a lot of things that can go wrong. But yeah, it's I think autonomous cars have much more. Mm, I think yeah, it's a very hard problem, basically.
Yeah, of course. I guess like if you are using your robot in a dynamic environment, like moving humans or objects, then that's quite challenging.
Mm.
If it's in a more static environment, then it is not that much problematic for the robots to.
Yes, yeah, especially if you have moving things, you have to be able to distinguish the map from or the surroundings, which are constant from something that is moving. I'm not sure how to solve that, but I will see. So I will I would just try to solve one problem at a time. And if I can get it working with only a static map without any, like with a static environment without any other things moving than the robot, then I'm happy. And then if that works well, I might move into also being able to deal with moving things. But I start with one thing at problem at a time.
Yeah, of course, that's a long story if you want to implement everything at the same time. But I think, as you said, it's a learning process for you. So
Yes.
you can. Um, the other question that I had was about the simulation. If you are not using ROS, let's say if you want to visualize what you see, do you have any solution for that?
Yeah, so this is still an open question. I don't know. I haven't yet decided about what what tools I will use for visualizing. For example, the 3D map, I guess.
You know.
Um, so I know that ROS has a lot of tools already for this. I haven't started using ROS yet because um, it's a very big framework, and I just want to start it with the bare things that I need. And I think it's also more interesting to start with that. But of course, and now like visualizing 3D and things like that, that might be, or more complex things might be, then it might be better to use ROS if they already have inbuilt tools, so you don't have to do a lot of things from scratch yourself. But yeah, this is still an open question. Um, they have at least this RViz tool and some Gazebo, I think, also for 3D simulation. Uh, this seems good, but I prefer to start very light and then build up. Um, rather
Yeah.
than having to learn a lot of things from some framework.
Yeah. Yeah, I think if you are not using ROS, then I can introduce you some of the very beginner friendly Slam simulator like VBots, for example, is one free 3D robot simulator which also supports LiDAR, camera, wheels, and IMU, and it's actually easy to script in Python and C++. So it could help you to basically visualize what you see, from the environment. So it's great for running
Okay.
simple EFK or sorry EKF or particle filter slam with custom code. And the another one is Coppelia Sim. This is also very physics-based simulator, which also supports Python APIs. And also, of course, MATLAB is another tool.
Yeah.
MATLAB Simulink has high-level visualization.
Yeah. This might be interesting. I mean, as long as it doesn't tie your hands to kind of having to implement your algorithm in a specific way. In a way, I just need to visualize this 3D map, and simulation might be interesting also. Um, just to test your, um, I mean, it's faster maybe to simulate a lot of different scenarios, but
Mm,
it's also a challenge to create a simulation realistic to
yeah,
the
true.
environment.
Yeah. I think rather than the ROS-based realistic simulators, as you said, Gazebo is one of them that works with ROS and ROS2 and supports real SLAM modules like Gmapping, Hector SLAM, Cartographer, and etc. And if you are really fan of NVIDIA, you can use Isaac Sim, which is basically GPU backed. But I think this is not free. So this is the Isaac Sim is not free, open source. I'm not sure.
Yes. Yeah.
Yeah,
This might. Yeah, there's. I have to look into a lot
yeah.
of tools.
Also, for the Python Slam simulator, there is also one PySlam. So it's a visual Slam pipeline for learning, of course. And this is also could be interesting for you to maybe take a look.
Yeah, yeah. I think I've heard about this Python. Yeah,
Yeah, yeah, that's cool.
yeah.
So what else remains? I guess we have talked about the hardware, the communication, the algorithm, and about the mechanical things. So what type of motor actually you're using?
It's a DC motor,
Mm-hmm.
just a very cheap one, and it has an encoder attached to it.
Oh, okay.
So
All
uh,
right. It's type of like what type of encoder it is? It's like a relative encoder or it's like um what's called
absolute.
absolute ones. Okay, yeah.
It's
Mm,
a relative one. It just gives you ticks. So
okay.
whenever it has rotated a certain angle, it will give a one tick, and
Mm-hmm. Understood.
then
Yeah.
yeah.
Yeah. Yeah, of course you need just to know the position. Yeah. Do you need as well to know the speed, or you just of course you can probably calculate from the distance and the position, also the speed. Yeah.
Yes, yeah, exactly. So there's many different ways to go around it, but go about it. But so at the moment, I'm just giving the speed of the wheels as one measurement of the system,
Yeah.
just based on the encoder ticks, and then I get acceleration from the IMU. So this is one. Um, measurements, and then I also have this angular velocity of the of the IMU, like how fast it rotates the whole of the IMU
Mm,
of the robot. And these so I'm not decided yet whether how much of these I use, whether I'm using I will use the accelerometer or not, because it's quite noisy and well, I think I'm just starting now as baby steps to use the IMU and the encoders and all the sensor data I have and see what I can get with that and how robust movement estimates I can get from that.
yeah, sure. All right. So you told me that you are building the structure with a 3D printer, right?
Yeah.
Which material are you using?
Uh, Actually, it was my colleague who printed this thing.
Yeah.
I think it's PLA, maybe
Okay, yeah,
PLA,
sure.
some very basic
Mm,
thing, but this seems to work well enough
sure.
so far. I think it's mostly just finding the design, which takes a few iterations because it's a lot
Yeah.
of trivial things which you are not always considering, like just the cabling is
Mm-hmm.
always something you overlook, and this is something that needs to be fixed still, and things like
Mm,
this in the 3D model. But uh, I
yeah.
hope this is not a big topic of this project. I just want to go on these algorithms as soon as possible.
Yeah, sure. And how big is it at actually the robot? How big is it?
Uh, well, it's uh, these computers are like sized like um, like a playing card, basically a packet of playing cards, and we
Mm-hmm.
have two of those. And then there's these wheels which are quite um, about the same size, and the camera. So, but a lot of cables also. So the whole thing is I don't know, maybe like uh, 15 centimeters times 10 centimeters
Mm, okay.
in
Yeah.
in the area of the thing.
Mm. No, that's a small robot, rather. Yeah.
Yeah,
Okay, nice. So, I think for this part, you just wanted to talk about the principle, the structure, and what was your plan basically. And then the next part, I would love to maybe meet you in person and you show me some stuff that you have done. So, I guess that we could make it like do it later, of course.
yeah,
Yeah, so until then you will work on your project, and when it is functioning, I would love to come by because yeah, we are living is not far away from each other, so I can come by and just see that how you
yeah,
have progressed.
yeah, yeah. Sounds good. So will this be like the whole one episode will be both parts in one, or
No, also we will publish this one first, the first episode that you have talked. That actually, what's your plan? Then the next episode, I will visit you to see the robot in practice.
yeah? But I'm just thinking that if something fails or something, it doesn't go according to plans, then I mean, this first episode, I guess the second one is the most interesting one. So
Mhm.
uh, it might be I don't know, like
Yeah, no
having one.
pressure.
Yeah,
So no pressure. I mean, like, yeah, we will see. So we will see. That's the that it's it for me. It's very exciting to see that, of course. when it
Yeah.
is functioning and working. But I got also a lot of information from you for this episode
Yeah.
that how you can actually make a slam-based robot. But as I said, if it is functioning, that would be quite interesting.
Yeah. Yeah. Okay.
All right. Okay, so I think your time now, and thank you so much for taking part. And until next time,
Yeah. Okay. Yeah. Thank you
see
too.
you.
Yeah. See you.